All right, this week we're going to be learning, or not learning Kirchhoff's rules. We've already studied those in combination circuits, but what we're going to do is apply it to multiple power sources. So if you have more than one power source or a battery or some sort of a power supply in a circuit, okay? So just as a reminder, we looked at Kirchhoff's rules already, that the total current going into a junction has to equal the total current leaving a junction or node. Okay, so this could also be referred to as a node. And then what's we're going to do too is the Kirchhoff's voltage law, that any closed loop, the voltage around must equal the sum of all the voltages within that same loop. And so we're going to do this zero. We could do it with a total as well. It just kind of depends on how we're looking at that second voltage source, as well as how we're applying or where that battery is. Okay, so I'm going to give you a few examples of that, and then in your check for understanding quiz, there's a few that you're going to actually write out, or not write out, but choose the correct one. And it's just looking at these here, but looking with the positives or negatives. Okay, so the positive and negatives are really the crux of the problem here. This image I took from your textbook, and I kind of like it and I kind of don't like it, to be honest with you. So essentially, if in terms of your voltage, okay, the voltage drop across a resistor is the potential difference between 2 points. Okay, we also know, thanks to Ohm's law, V equals IR, and so we can refer to our voltage drop as the current times the resistance. So if the current is going in the correct direction, and the voltage drop should be negative. Okay, if the current is going in the opposite direction, then we're going to end up with a positive. All right, and then same thing, the opposite is going with our the direction of travel through a battery. Okay, so if we're looking at the current going through the battery in this direction, we have a positive. If it's going the opposite direction, we end up with a negative. Okay, so this will kind of make sense as we analyze them. I'm going to go back to this slide here. And so what we're going to look at, and again, I really try to find a lot of different circuit diagrams to depict this. So some of them I really like and some of them are okay. So what's happening here is that with these two batteries, remember, we're using conventional current. And so we're going from positive to the negative. So you can see this loop here is how we're actually going to travel. And then this loop here goes out and around like that. All right, which means that I've got current coming in here. This one I don't really like because it doesn't follow the way that I have this. So the way that I would do, well, this is a bad example, but the way I personally would write this one is that I've got this current going in here. And then based on the way that this is drawn, it looks like I should have this current going in there, which means I'm going to have a specific current coming out. And so if this is my I1 is going in, my I2 should technically be going into that C junction. And so I'm going to label this I3. That means my I1 plus my I2 needs to equal my I3. All right, so that is that junction rule. Okay, so let me erase all of this. Okay, so let's take a look at our voltages. I'll do this in a different color here. Actually, that's not a good color. Here we go. Sorry, indecisive. So what we're going to do is, first of all, we're going to pretend like this doesn't exist. Okay, and so I know that E, and so this symbol you may see a lot too, that is the EMF, or the electromotive force. It is the total voltage of the circuit. So it's kind of differentiating that. You can use either one. I still personally like to use V total. So I know my V total is going to equal my V across R1 plus my V across R2. So instead of writing it this way, we're going to write it that my V total minus V1 minus V2 is going to equal 0. So that's how the Kirchhoff's rules kind of state that the sum of any loop should equal 0. Okay. Now, instead of V1 and V2, because that's more unknowns that I know, or that I don't know. Okay, we're going to start to use Ohm's law, and I know that my I times R is my V. So I'm going to rewrite that my V total minus I1 R1 minus, over here, this is I2 and R2. I2 R2 is going to equal 0. Okay? So that is now our statement, and then we could actually put some numbers in there. So we could have 20 minus 10I1 minus 4I2 is equal to 0. Okay? So that is for this first loop, this ABC loop. And now we're going to look at it in terms of the DAC loop over here. So let me pick a different color. And so what I'm going to do here is that I'm going to skip kind of right to this line that I know that my V total in this case is going to be, now this we said was I3. So it's going to be minus I3R3 minus I2R2 is equal to, I'm running out of space, but that's equal to 0. Okay, because if we're ignoring this side, then we're looking at this loop that's going around here. Okay, so I now have 12 minus I 8I3 minus 4I2 is equal to 0. Okay? So this is the basis of what we're going to be doing. That was a lot of information to get to where we're going here. So now what we're going to do, I'm not going to completely solve this one, but you're more than welcome to. I've got what do I have here? Nothing's working. Here we go. 1, 2, 3 equations with 3 unknowns. Okay, so what I'm going to show you guys how to do is set up this one in terms of I2, and I'm going to set up this one in terms of, this one in terms of I1, and this one in terms of I3, so we can plug it into here. Okay? All right. Hopefully I didn't lose you by now. So looking at this example here, okay, very similar. They're all going to be very similar. And you can pick which loop that you actually want to do. So I personally like to stick to try to have one total voltage. So I would use loop 1 or loop 2. But the other thing you could do is use this loop 3, where this is where you need to decide what direction you're going. I know that my 20 is bigger than my 10 volts because these guys are going to go, they aren't necessarily going to work together, but I can show you both ways on how to write these specific equations. Okay, so let's take a look at our loop 3, the way that it is written, going in this direction. Okay, so I would do this as V1, or it's kind of confusing because it has both those V's there. Let's go with 10 volts. Okay, so this is what I mean that my current is going in this direction. It's going the way that it's supposed to, so it's positive. Okay, when it goes through a resistor, the way it's supposed to, that's a voltage drop. So that's going to be I1 R1. Okay, and then we're going to keep going here. So now notice that my I should be going this way, and I'm going the opposite as that it wants to. So this is where we're going to add I2 plus R2. Same thing here. This is going the opposite direction as it should. So I'm going to add those 20 volts, and all of that together should add up to 0. So that's how I deal with this big third outside loop. Okay. Yeah, but that's where I would personally stick to loops 1 and 2. But you're more than welcome to do that third big loop if you want. All right. I'm not sure what happened to all my notations here. Okay, but once again, what we're going to do is you're going to pick a loop. So the last two cases, the loops were drawn for us. My suggestion is to look at your battery and don't make things harder for yourself. Okay, and so in this first situation here, part A, and this is the same circuit except for V2 is flip-flopped. All right, so you know convention current goes from positive to negative. Okay, and so same thing here, we go from positive to negative. All right, so you know these two batteries are kind of working together, so you can kind of treat them, you know that it's going to work together, you're not going to get up any negative currents at all. In this one here, we've got this one going this way. I would actually draw this one in that direction. Okay, so you know in this case, the way that you're doing your currents are going to be different here. All right, and so just pay attention to those. If you accidentally draw this one like this, that's all right. Your end answer might end up, you might end up with a negative current, and that just means you drew your arrow the wrong way, or you drew your loop the wrong way. One of the examples on this PowerPoint is going to show you that, or I'm going to show you that, so we can deal with that. Okay. All right. So let's go ahead and tackle this guy here. Okay. So there is a lot going on in terms of how we solve this. So please, be patient. If you do know, with 3 equations, 3 unknowns, if you know matrices or how to do a matrix, you are allowed to use those by all means. I don't teach that, but if you are in advanced enough math class to know what I'm talking about, please feel free to use that. Okay. Anytime you learn something in math, you're learning a tool or a skill to be able to apply in these other courses. So if you're capable of applying these matrix rules, then please, by all means, go for it. Okay. So here we go. We've got a 10 volt, a 5 volt, and then 3 resistors. So this is pretty much a basic one that we can do. And so I'm going to create my loops that go with the conventional current. We don't know that this is always going to be 100% right, but that's where I'm going to start. Okay. So based on that loop, I know I've got a current going through here, and I got a current going in here, and then I've got a current coming out. So that's my junction rule. Now, here is a really big difference in what we were doing compared to where we're going, okay? The current that goes from this battery into this junction, out of this junction here, is one current. In the past, we've been labeling I1 that goes through R1, I2 that goes through R2, and so on. But in this case, we're going to label our current by loops. So once again, I know I've got a current going through here that comes back around to here. Okay. And then I have got a different current that is coming through here. So when we're doing these loop rules, you're not going to have I1, I2, I3, I4, I5, I6, and so on like we did in the combination circuits. Instead, we're just going to have 3 I's, unless we're doing an even more complicated one, but I do not think I gave you one that complicated. Okay, so we're starting off basic, but if there was another resistor here, let's say, both R2 and let's call this R4 would get the same current, and I'm calling that I2. So we're not going to have an I4. We are just going to have 2 I's based on these loops and these colors here. Okay, so I know to start everything off, you need to figure out your current statement, which my I1 plus my I2 is going to equal I3. Okay. Hopefully you can see that from the arrows. So now I'm going to do my 2 loops. Okay, so I'm going to start with my 10 volts. All right, so I know my V, I'm going to call that 10, minus my V across R1, minus, because it's going in the correct direction, my V across R3 is going to equal 0. All right, so now I'm going to substitute my numbers in there. So I'm going to have 10 minus my V1, which is also getting my V1 is also I1 times R1, and my R1 is 20, so I'm going to do 20 I1 minus 10 I3 is equal to 0. Okay. So my next loop is going to be, and I'm going to leave a little space because we're not quite done with that loop yet. Okay, my next one is going to be the 5 minus I2 R2. I'm writing this a little bit different. Sorry, I3 R3. So here I wrote it in V's. Here I'm writing it in IRs. Okay, but regardless, we need to get to the second part anyways, which is 5 minus 50I2 minus 10I3 is equal to 0. Okay, so now we've got our three equations, 1, 2, 3. Three equations with three unknowns. So my matrix people, go for it. Everybody else, what is the one thing that they all have in common, which is I3? So we're going to put both our blue and pink equations there into terms of I3. Okay, so I've got my blue pen already, so I'm going to go ahead. I want I3 in the equation, which means I need to isolate I2. All right, so if I subtract that to the other side, I'm going to end up with 50 I2 is equal to 5 minus 10I3. Okay, now I'm going to divide both sides by 50. Please be careful about this. This is math that you learned back in middle school, but we don't use it that often. Your 50 and your 10, yeah, that's nice, but it's the whole thing is divided by 50. So this is a subtraction. So just remember your rules, please. So your I2 is going to be, what is this, 0.1 minus 0.2 I3, okay? So this pink one here, I didn't leave myself that much room. So I'm going to go ahead and kind of talk you through it. I'm going to isolate I1 in this case. All right, so my I1 is going to equal 10 minus 10I3. And then I'm going to divide both sides by 20. So I'm going to end up with I1 is equal to 0.5 minus 0.5 I3. Okay. So now what we're going to do, I know this is what I1 will equal, and I know this, excuse me, is what I2 equals. And so I'm going to plug those into this equation for I1 and I2, and then that way we're left with all I3s. Okay, so I'm going to do that over here in white. So my I1 is, whoa, that's not what I wanted. 0.5 minus 0.5 I3. And I'm just using these brackets just to show you that that's what this is. And I'm going to add I2, which is 0.1 minus 0.2 I3. And that all equals I3. Now notice these are addition or subtraction, so we need to consolidate our like terms. So I'm going to add my 0.5 and my 0.1, so I get 0.6 minus 0.7 I3 is equal to I3. Now this is 1 I3, right? And so we don't usually write it like that, but that's what it is. So I'm going to add that to the other side. So I get 0.6 is equal to 1.7 I3, and then I can solve that. My I3 is 0.35 amps. Okay, so I now know what one of these are. I can go back in to these other equations then and solve them. So my I1, I'm going to do 0.5 minus 0.5 times I3, which is 3.5. When I do that, my I1 ends up 0.325 amps. And then if I plug my 0.35 into here to solve for my I2, I get 0.03 amps. Whoa. Sorry. I'll write it down here. I2 is going to be 0.03 amps. Okay. So now I know all of my currents. So if you want to double check, okay, if I go back to this original equation here, I've got 0.325 plus 0.03, and that is pretty close to 0.35, which is my I3, okay? Now it asks for you to solve for your voltage drops too. That is just going back to V equals IR, and so for my voltage drop across R1, I would do my 0.325 times my 20, and so on. Okay, I've kind of run out of space, and that one should be pretty obvious based on our previous work on circuits. But again, you just use your Ohm's law for each individual circuit. Okay? So lots of work here, but it's not difficult work. You just have to figure out your three equations. Okay, so you need your current equation, and then using your voltage loops, you're going to get the individual currents to plug in there once you get your three equations with three unknowns. All right. Okay. Hopefully you're hanging in there with me. We're going to go ahead and do this one more example. Okay. This is very similar to last, but it's a little bit different. Okay. So once again, I'm going to do this loop. And then this one's kind of drawn funny. My negative's on this side, even though my battery is actually drawn backwards on this. I'm going to go ahead and draw my loop like this to show you what happens. Okay? So those are my two loops, which means my current, I'm going to use this junction C as my current statement. So I'm going like this and like this. I'm going to make this... this loop here is going to be my I1. This loop here is going to be my I2, which means, again, if there's multiple resistors in there, they all are I2. And then this is going to be my I3. Okay, so it's very similar to the last one where I'm going to have, for my current statement, I1 plus I2 is equal to I3. All right, so let's go ahead and figure out my voltage. So for the first loop, I've got, and I'm going to jump right into it, knowing that this is my total, and this could be written as I1R. All right, these aren't quite labeled R1s and R2s, so I'm going to just jump right into it. I'm going to label this R1, this R2, and this R3, just in case anybody's confused. All right, so I'm going to go ahead. My first loop, I have 80 minus 20 I1 minus 40 I3 is equal to 0. Okay, for this second loop, I've got 40 minus 10 I2 minus 40 I3 is equal to 0. Okay, so once again, we're comparing. Those are my three equations with my three unknowns. I'm going to go ahead and solve them by putting them all in terms of I3 once again. So in this case, my I3 is going to, nope, just kidding. I'm not putting it in terms of I3. I want I3 in the equation, so I'm going to isolate I1. All right, so it's going to be, I1 is going to be 20 I1 is equal to 80 minus 40 I3, which, I'll just write it out. So that's over 20, which means my I1 is going to be 4 minus 2 I3. Okay, so same thing here. I'm going to isolate I2. So my I2 is going to be 40 minus 40 I3, all divided by 10, which gives me 4 minus 4 I3. All right, so now I know I1 in terms of I3, and I know I2 in terms of I3, so I'm going to plug those in. whoops. Sorry. Let me start over. Sorry, not start over. I'm not starting. I'm just going to rewrite this. Okay, so instead of I1, I've got 4 minus 2I3 plus 4 minus 4I3, which is equal to I3. Okay, when we put this together, I've got 8 minus 6I3 is equal to I3. So when I add that to the other side, I've got 8 is equal to 7I3. So I'm running out of room again. I'm going to go down here. So my I3 is going to be, as I said, I've got 7. I3 is equal to 8. So my I3 is 1.14 amps. Okay. Be careful when you're adding. It's like sometimes my students forget how to add negatives or isolate when we're adding and subtracting. Everybody wants to divide things out. So I know it's such a basic skill, but we haven't always used it very often. So just be careful with that. Okay. All right. So now I'm going to plug my I3 back into this equation. So my I1 is now going to be 4 minus 2 times 1.14. So my I1 is 1.72. Okay. And this may start to ring like, interesting, because my total I3 is less than that. All right. And so we're going to show you why. So my I2 is 4 minus 4 times 1.14. All right. So my I2, I actually get a negative number. I get negative 0.56 amps. All right. So what does that mean? That means I drew my second loop backwards. Okay. So I drew it as if it was going like this, but this is telling me that my current is actually going the opposite direction. And that is completely fine. Okay. And the reason that it is in the wrong direction is because these plus and negative signs. So when I did this one, these, I went based off of the symbol, and I didn't originally look at those, but once I did it that way, I thought this would be a very good learning example, that if you end up with a negative current, that's okay. It just means your loop was drawn in the wrong direction. So I should have gone positive to negative here. But again, all my numbers are correct. I just know logically that this is going to be a 0.56 amp going through that. Okay, because then if we go back and actually test our theory here, that I1, which is 1.72, plus I2, which is negative 0.56, is equal to I3, which is 1.14, and it does in fact work out. In fact, I think it actually ends up being 1.16 when you do this, or when, I can't remember, but I've got it on my calculator right here. Yeah, 1.16, which is pretty close to 1.14 with some rounding that we had to do. Okay. So that, in a nutshell, is how we do, or how we apply Kirchhoff's rules to combination circuits. All right, so now this one, I'm not gonna go through this one. Well, I need to assign some values, but I'll do that in a different video. What I wanna do is show you your loops though, okay? Because this one has more than just 3 resistors. All right, so first of all, I'm gonna make, this is my junction and this is my junction, okay? So, or node, sometimes they're called nodes. So if I go out of my positive battery here, and it's gonna come back around. Okay, so I would call all of that I1. So that is my I1 loop. So we're no longer doing I1 goes with R1, and so on. So anything in this loop is going to get I1. So R2 and R1 both get I1. Okay. My second loop I would do here until I hit the node, and then after the node and back. All right, this one I am going to call my I2 just like I did before, which means my R5 and R4 both get I2. And then my last loop, is this one in the center here. Okay, and I'm going to call that one I3. So we only have 3 currents. All right, so before when we were doing combination circuits, you guys were listing out all the different currents for each individual resistor. Now we're just labeling all those ones in series with the same current, okay? So if I go to do my voltage for my purple loop here, I would do V1 is, whoa, not equal, sorry, minus I1R2 minus I1R1 is equal to 0. So as I go around here, I can't include, oh, just kidding, I do include that one. Let me start over. Just because I like it to go in order. So this is my loop here, not just I1. So I've got I3R3 minus I1R2 minus R1. Let me be consistent here. I1R1 is equal to 0. So notice that if you start labeling these as individual I's, you're going to have way too many unknowns. All right, so now in this situation here, we still have our I3 that we're going to try to isolate, not isolate, but put in terms of. And so we're going to isolate these 2 guys here. To go any further, I would have to know the resistances of these, but you would simplify it in that way. Okay, so same thing for my V2. My V2 minus I2R5 minus I2R4 minus I3R3 is equal to 0. Okay, so once again, your I2s are going to be the same I because they're in the same loop, right? They're in series. They're going to have the same current. And so again, I would need to know the resistors, but you could simplify those, making sure you got that negative in there. And then we have R3 in both equations. So I would end up with I1 is equal to, and whatever that is in terms of, and then I2, whatever that's in terms of, and then I can use my I1 plus I2 is equal to I3. This isn't always the case, but this is how I kind of keep drawing them. So sometimes your equations are going to have, or your circuits are going to have loops or labels on them, and so follow those. If not, that's kind of how I do that one, is that you've got I1 in one loop, I2 in another loop, and I3 is the one that's kind of combined in that center branch there. Okay. So I hope that helps with Kirchhoff's laws. Please read through again the text that the recommended sections that I've posted. Gives you lots of examples on how to do this. There is also a practice worksheet as well as an answer key with full solutions. I will also walk through some of those solutions, and please reach out if you need any extra help.